Hi everyone, welcome to module number 2 for CNEAS 7103 Design and Analysis 1. In this module we're going to be talking about definitions of error and how we're going to make parameter estimates from the data that we observe in our samples. So first, as a reminder, we're using the general framework of data equals model plus error, which we can write more mathematically as y sub I, right? Each individual data point is equal to b0, which is our estimate from our model, plus some amount of error, or e sub I, which is a unique error for each person. This error can be rewritten, right, as the difference between our prediction and the observed value, right? So just doing a little transformation of the formula above, we can say that each data point, y sub I, minus our estimate, or b0, is equal to e sub I, right? So this is the error that is left over. It is the difference between what our model is predicting and what we actually observed. And written in this way, it's pretty easy to see that this error is a value that's been left over or that remains to be explained is another way we might talk about this. So as such, errors of this type are often referred to as residuals. So we might talk about residuals or residual errors, but that's really the same as these epsilons in our model. Now, first, we have to, before we can calculate that b, right, in order to calculate that error, we have to fit our model parameters. That is, we have to find some value of b that's going to be a good estimate of our beta. But what value of b do we want, and how do we choose it? Well, recall that b is an estimate of beta. So intuitively, b first needs to be a good explanation of our data. If we pick a value of b that leads to large errors, then it's not a good explanation of y, and it's probably not going to be a very good estimate of beta either. Now, intuitively, we can think about this as if I was just to pick a value for like heights of people in the room, and I pick 250 centimeters. That's not going to be a good estimate, and that's going to lead to very large errors. So we have two options there. Either that b is a bad estimate of beta, or if it is a good estimate, if the true beta, if the true sort of typical human height is 250 centimeters, then I just have a sample of very, very short people, right? So we're going to need to do a little bit more work to really understand the relationship between b and beta, and we'll do some lab assignments in which we'll simulate sampling distributions to show why this is the case. But intuitively, it makes sense that our parameter estimate should be a good description of our data. Because if it's not describing our data well, is it really going to be a good description of what's happening in the population? Now, this doesn't always mean that b represents beta very accurately, right? As we talked about in small samples, we can get values of b that are very bad estimates of beta. But our data are all we really have to go on. So sort of the first step that we need to take is to make sure that the value of b that we choose is a good explanation of the data that we can physically observe. And then, as I said, in our lab assignments, we're going to look at some sampling distributions to talk about how the relationship between b and beta depends on things like the sample size and the variability inherent in the data. So first, let's think about a few different methods for calculating errors, because we're going to choose a value of b that gives us the smallest amount of error. But smallest amount of error can be defined in a few different ways. So for instance, if I as a teacher wanted to estimate the number of books my students read over the summer, I have a very simple model where I have y sub I, which is the books that the students actually read, is equal to some value, my estimate of how many books they read, plus error. So before I actually see the data, before I see how many books my students read, maybe I'm a very pessimistic teacher and I think they didn't read any books over the summer. So I'm going to estimate 0 for everyone. I have an unconditional model where b is equal to 0. That's going to lead to certain errors, right? So here's our column of residuals. And one way I could calculate these one way I could calculate an index of error is to take the sum of absolute errors. Now I would take absolute errors because then I wouldn't have to worry about positive and negative errors canceling each other out. All errors are going to count equally. So sum of absolute errors intuitively seems like a reasonable way to do this. And what I would find then is that by the sum of absolute errors, if I estimate 0, I get 32. Now, maybe my pessimistic estimate isn't great, right? Certainly 32 seems like a lot of errors. So maybe I take an optimistic estimate. Maybe I'm a teacher who thinks my students are really intrinsically motivated, and I'm going to estimate they all read 10 books over the summer. Well, now this is going to lead to a very different distribution of residuals. You can see now we have a mix of negative and positive residuals. But if I take the sum of those absolute values, I get 26. So again, better than the pessimistic estimate, but this seems fairly errorful. 26 is a lot of books to be off by. So maybe I take a more moderate estimate. Okay, so if I estimate 5 for everyone, you can see again that I have a distribution of negative and positive values. And if I took the absolute value of all of these and then added them up, right, as per our formula, I would get 19. So this is a much better sum of absolute errors than either of the other two. It's still not super accurate, right, as there's quite a bit of variability in the books that our students read, but it's given us the smallest sum of absolute errors of the values that I looked at so far. And if we were to do this for lots of different numbers, we would get a distribution for the sum of absolute errors. And what we would find is that it looks something like this. We would get a U-shaped, or in this case, kind of a V-shaped curve, where we have the sum of absolute errors for many different values of estimates. And you can see that we get the smallest sum of absolute errors at 5. And now 5 also happens to be the median of our distribution of scores, right? We had 1, 2, and then 5, and then 1, 2 to the either side of it. So 5 is the middlemost score in our distribution, making it the median. And an interesting property of the median is that it will always produce the smallest sum of absolute errors, regardless of the distribution. And we can see that by changing one of these scores. So we're going to change this 14 to a much larger value. So let's say instead of 14, this student read 140 books. Maybe that's a data entry error, or maybe this is just a super motivated student, or maybe they count comic books as books, right? Whatever the reason, this person has 140. Now, the median does not change because the median is the centermost score in a distribution of scores. There's still just 5 scores. So even though this one is now 10 times larger, the value of the median doesn't change, and the property of the median does not change. It's going to give us the smallest sum of absolute errors. The absolute errors are now all quite a bit bigger, right? We're off by a lot, but you can see that it's still going to give us the best estimate, whether we're moving to the left or the right. And now the way we would think about this is that the sum of absolute errors is an estimator. It is a method for giving us an estimate. So if we use the sum of absolute errors as our estimator, it will always return the median as the best estimate. And in lab, we'll work through some assignments to show why this is the case. But the median is always going to produce the smallest sum of absolute errors, even if I have a skewed distribution like this, where I have one very, very positive outlier. An alternate approach, though, if we didn't want to take the sum of absolute errors, would be to take the sum of squared errors. Squaring has a lot of appealing properties, right? It's going to remove the sign in the same way that taking the absolute value does. But it's also going to make big errors even bigger, right? Which we can see in this example over here. Again, we're going to use my pessimistic estimate of 0 books read over the course of the summer. So we estimate 0 for everyone. You can see that we have a distribution of errors. And now if we square them, 1 stays 1 because 1 squared is 1. 3 becomes 9, and 14 becomes 196. Okay, so not each error counts the same now when we're taking the sum of squared errors, and actually we penalize large errors more. So we're going to if we were going to start using the sum of squared errors as our estimator, it's going to be sensitive to the magnitude of these scores, which we'll see in just a second. All right, but first let's just walk through calculating the sum of squared errors here. Right, again, I have the actual number of observations. I have the estimate, in this case my pessimistic estimate of 0. I get a residual for each person. I then square those residuals, and if I sum all of the squared residuals, I get 312. So the sum of squared errors for this estimate is 312. Now, if we switch to my optimistic estimate, right, I estimate 10 books read for each person. You can see we get a distribution of positive and negative residuals. Again, if I square all of those residuals and then add them together, now I get 172. So my sum of squared errors is 172, quite a bit better than the previous sum of squared errors. 10 seems to be a better estimate than 0. What if I take my moderate estimate? Okay, so again, we're going to estimate 5 for each person. We're going to calculate the difference between the observed data and our prediction to get a residual. We're going to square the residuals, and then we're going to sum all of those residuals together, and we get 117. And if we did this for lots of different numbers, what we would find is that the smallest sum of squared errors is no longer the median. In fact, the sum of squared errors has been pulled to the right. And you can see that the sum of squared errors for this, or the value that gives us the smallest sum of squared errors here, is 6.4, which happens to be the mean of all of these values. And the mean is always going to produce the smallest sum of squared errors. Or sort of the other way to think about this is our sum of squared errors is our estimator, right? So if we want the estimate that gives us the smallest sum of squared errors, that will always be the mean. So if we use the sum of squared errors as our method of estimation, the mean is always going to be the best value if it's an unconditional model. It's going to give us the smallest sum of squared errors. Now, this might be slightly errorful, right? So we see that we have 107.2 is our total sum of squared errors if we estimate the mean. But that's better than any prediction to the left or any prediction to the right. Now, one important property of the mean that's distinct from the median is that it's going to be sensitive to outliers in our data. So now if we change this to 140, like we did before, you can see that our mean changes from 6.4 to 31.6. And the reason for this, right, is again, the median is the centermost value of a set of numbers. The mean gives you an equal mass of error to one side or the other. It picks the center of a mass of numbers, right? So it's sensitive to what those numbers actually are. The median is sensitive to the number of numbers that there are. The mean is sensitive to the magnitude of those numbers, right? So if we actually change the magnitude, you can see that we are going to shift our mean, and our mean follows that positive value in order to create a larger error. So there's larger distance, right, between the numbers below the mean, right? It's moving away from 1, it's moving away from 3, it's moving away from 5 in order to move closer to 140. And it's going to move proportionally closer to that outlier in order to give us the smallest sum of squared errors. So again, the mean is sensitive to outliers, but even in this skewed distribution, the mean is going to give us the smallest sum of squared errors. So it's still the best estimate if we use the sum of squared errors as our estimator. So now when we're describing these errors, we've talked about the sum of absolute error, or we've talked about the sum of squared errors, but total error is not always very useful because larger samples are more likely to produce more error, which you can just think about sort of conceptually. If I have 10 scores and I calculate the sum of squared error, that's probably going to be smaller than if I took the sum of squared errors from 100 scores, simply because there are more scores. So when I take the sum, it's going to be bigger. So total error isn't always useful. We want some way to standardize those sums with respect to the sample size. So for the sum of absolute errors, you could take the median absolute error, or for the sum of squared errors, you could take the mean squared error. You could calculate the average squared error. And we'll focus on the sum of squared errors because, as we'll discuss in Chapter 3, it's a more efficient estimator a lot of the time for the type of data that we're going to work with. So let's focus on the sum of squared errors for the moment, right? And again, we're going to have this total sum of squared errors here, but we want to standardize it to our sample size. So whether we have 10 observations or whether we have 100 observations, we can kind of say per observation, how much error is there? And to do that, we're going to calculate the mean squared error, which is the sum of squared errors divided by the number of observations that there are minus the number of estimated parameters. So if we wrote that out, right, here's our formula for the sum of squared errors. We're taking each score minus the estimate, squaring that residual, or squaring that deviate, and then summing all of those squared deviations together. And then we're going to divide those by n minus p, where n is the number of observations and p is the number of estimated parameters. This is also, the mean squared error is also described as the variance. And you might have encountered this statistic before. You've almost certainly encountered the root mean squared error, which is just the square root of the mean squared error. But here's the formula for that. This is more commonly referred to as a standard deviation if we're calculating the distance between individual scores and the mean. So when we're looking at these things with respect to the mean, well, these are the variance and the standard deviation. We can more generally, though, also talk about them as the mean squared error and the root mean squared error if we're using other types of predictions rather than just the mean. So if we are estimating one parameter, right? So if we have an unconditional model where y sub I is equal to beta 0 plus epsilon, we're estimating one parameter, right? Beta 0. So we're going to fit a value of b to go in there. So n minus p in that case is really n minus 1 because p is the number of estimated parameters. We are estimating one parameter. So we can simplify this a little bit to say that we have n minus 1 in the denominator here. Additionally, we know that the best fitting estimate is going to of beta is going to be the mean of all the observations when we're using the sum of squared errors as our estimator. Thus, for each person, we predict the mean, right? So y hat is going to change to y bar, and we're going to predict the mean for each person. And so we can rewrite this formula as the sum of squared errors, right? So we have each observation, y sub I, minus the mean. We square those deviations. We add all those squared deviations together. We then divide by n minus 1, right? So we have our number of observations minus the one parameter that we're estimating, which is the population mean. We've calculated the sample mean in order to estimate the population mean. So we have n minus 1 in the denominator. We then divide the sum of squared errors by n minus 1. That would give us the mean squared error. If we want the root mean squared error, or the standard deviation, we're going to take the square root of all of that. And this is the formula for the standard deviation that you've probably encountered before. And we're going to spend some time in lab to show you why we divide by n minus 1 when we're calculating this in a sample, and why it's actually dependent on the number of parameters that you estimate. Right. For now, the most important thing is to remember that it's n minus 1 in this calculation because we're estimating one parameter. But in the lab, we're really going to try to show you why that's the case. Okay, so that's it for this module. I hope you understand why we like sort of the mean and the median, because they'll give us the smallest sum of absolute errors and the smallest sum of squared errors. And this hopefully introduces you a little bit more to the idea of how we're going to calculate errors and how we're going to have estimates of error based on what we observe in our samples. So in the subsequent chapters, we're going to talk a bit more about using this in an inferential way and how we actually expect B to relate to beta and how we're going to start using some of these error calculations to really compare our models and decide which model is better than another.